Doctor, I'm gonna unmute yourself. Doctor, I think you forgot to unmute yourself.
Okay, thank you, Kyla. Kyla, sorry. Okay, again, so good morning, everyone. So I hope you are fine. So we are in the second week of the lecture. All right. So last week, so we stopped at the position time graph. So where we learn about the relationship between the velocity and the displacement. All right. And then also according to the specific time. So we already learned about the instantaneous velocity, about the instantaneous acceleration, okay, and then we already plot the graph on the xt, okay, where the x is the displacement and t is the time. All right, and then today we're going to continue further, all right, with the equation of motion, right? So this is what we already derived, okay, for the acceleration, okay. So we have, let's say, from previously, we have Vx. So Vx is the velocity at any location, all right, equals to V naught x. So V naught is equals the starting position, all right, of the velocity, all right, the velocity at the starting position where we are measuring at initially, all right, and plus ax t, and then t is the time that has elapsed, right? So we need to measure the acceleration between v naught x until at time t. Okay, so that's how we define the vx. All right, and then we have x. Okay, x is equals to x naught plus v naught x t plus half ax t squared. Okay, so x now becomes the displacement. All right. So okay, from there we can also know what is our v squared x. Okay, so v squared x. Okay, so basically we are expanding from equation 2.8. So we have v naught x squared plus 2ax, okay, and then the difference between x minus x naught, okay. So basically we include equation 2.12 and 2.8 into 2.13. Okay, so basically it is actually, when you make this, is the equation should be v naught x squared plus 2 v naught x ax t, okay, plus ax squared t squared, okay, because that one already been simplified, okay, by x over here. All right, so x minus x naught, so you obtain this, okay, you obtain this term. Okay, this is the term that you obtain. So for this one here, okay, so when you multiply back, you look there, so you have ax squared, all right, times 2, okay. Okay, so you have ax squared t squared, and then also 2 v naught x t, okay, ax. All right, so that's actually equals to that. So basically this one is equals to vx equals to v naught x squared plus 2 v naught x a x t plus a x squared t squared. So that's basically, okay, so that's basically similar to that. Okay, and then this term is equals to that. So that's how you derive equation 2.13. Okay. All right, so for this one, so this is actually also you can get that equation. So you just bring that this x node to the other side of on the left hand side, okay, and then you obtain this. Okay, you obtain that, and then actually you just take out t from there. Okay, take out t, and then you left. Okay, you left with this term. Okay, and also this term. Okay, so from there, okay, you later, okay, you later use this, okay, to make it equals to this one. Okay, all right, so that's how you obtain those equations. Okay, so I hope that's clear. All right, so there are 4 equations of motion that relate with the constant acceleration. Okay, meaning that it accelerates at the same value, okay, from time t naught, right, to t1, t2, and so on. Okay, so that's actually the meaning of this equation. Okay, so you also have the term of free fall. Okay, so the free fall is the motion of an object under influence of only gravity. Okay, as you can see from the figure on the right side, so you have a strobe light, okay, flashes with equal time interval between the flashes. Okay, all right, so you can see that the velocity change in the same in the each interval, so the acceleration is constant. Okay, so you have that the equation for acceleration, all right, the equation for acceleration for the free fall object, you learn that it is accelerated at 9.8 meter per second squared, right? So that's actually the constant acceleration. Okay, so the acceleration actually doesn't increase. Okay, it doesn't increase even at the starting of having the velocity until it reach the ground. Okay, you look for example here. So we have again the example of you are dropping an object from a pizza tower, as we learned last week. So okay, at initially, all right, initially, of course, because the object doesn't move, so we have the v naught is 0. Okay, and then we have t also at 0 and y also at 0. Okay, but once it moves, okay, so we will have the value, right? We will have the value for different velocity, okay, until it reach the ground. Okay, so the acceleration between those time is 9.8 meter per second, which is equivalent to 32 feet per second squared. Okay, so let's run this example.
Example 2.6, a coin is dropped from the leaning tower of Pisa and falls freely from rest. We'd like to calculate its position and velocity after 1, 2, and 3 seconds respectively. We'll begin with a diagram of the problem. So the coin is dropped from this level, and of course it falls down to ground level. And the first thing we'll need to do is choose a coordinate system. I'm going to take the positive y-axis as actually up, as one usually does, and we're going to choose the initial position of the coin at y equals 0. So here's the origin on this axis. Our task is to calculate the position at t equals 1 second, 2 seconds, 3 seconds, and the corresponding velocities. To execute a solution, I'll use the free fall equations, where since the coin starts at rest and at the origin in the coordinate system, I'm going to take y naught to be 0, y naught is, v naught y is equal to 0, and I'm only left with the acceleration term, which is minus 1 half times minus g, and I get this expression for the position. Likewise for the velocity, the initial velocity is equal to 0, and I just get minus g times t for the velocity. Using these two equations, I can fill out a table of position and velocity at these respective times. Here are the entries. And I notice that all of the entries are negative, and the reason that's true is I took the positive y direction as up. If I'd taken the positive y direction as down, in that case, AY would have been equal to plus G. And the positions would have actually been positive also, and in that case, all of these entries would have been positive. And this ends example 2.6.
Okay, so I hope that is clear. All right. So you can hear my voice?
Yes.
All right. Okay, so basically, so what we learn from this, so we use the equation that I just discussed with you. So basically, V naught will be 0, and then V naught y, because the starting position, of course, the velocity will be 0 at time 0. Okay, so what's left now with the AY? Okay, as I just said, so we have the constant acceleration, but because we are considering the y, okay, downwards, which is towards the negative y, so we are using the minus g. Okay, so that's how we obtain that. All right, so half of 9.8, so we have 4.9, so it's minus 4.9 e squared. Okay, all right, and then we have the another equation. So we use the Vy. So Vy is the velocity at a position y. All right. So to know that, okay, so we have the v naught y. Of course, that is 0. Okay, and then we have ay t. Okay, so we are using this, okay, these two equation, all right, to obtain the position and y velocity. All right, so basically what you need to do is just adding the,
Equations that can fill out a table
okay,
of position and velocity at these respective times.
so basically you just insert,
Here are the entries.
all right, the time. So time
Now
1
notice that
second,
all of the entries
right,
are negative.
2
The reason
seconds,
that's true is that
and
the positive
3
y
seconds,
direction is up.
and
By
then
taking the
you
positive
get
y
the
direction as down,
position.
in that case, AY
All right, for
would
example,
have been
at T1, as you can see, so you insert 1 over there, right, and then you obtain at 1, so you got the value as minus 4.9 meter. All right, and then you have the, all right, so you already, okay, now you want to know the y velocity, so that's equals to Vy. Okay, Vy is equals to minus 9.8, okay, times t. So times 1, right? So you obtain the y velocity. Okay, and then do the increment. Okay, now you insert 2, so you got 4 times 4.9, so you got 19.6. All right, and then t now equals to 2 for the y velocity, so we have 19.6. And so you do the similar thing with at time 3 seconds. Okay, so I hope that is clear. Okay. All right, so you also have the up and down motion in free fall. So basically, the position as a function of time for a ball thrown upward with an initial speed of, for example, 15 meter per second. All right. So actually, the ball will okay, the ball will go up first, and then later it will go down. Okay, so let's have a look on how to solve that. So basically it is like this. Let me get you an example. Right. So basically the ball, okay, so the ball is actually, so you assume that this is like a ball, right? So the ball moves outward, and then because due to the gravity, so it will drop. Okay, it will drop. So again, so you push it up, okay, you throw it, okay, you throw it outwards, and then it will go down like that. Okay, so basically that is what is described by the example. Right, so we look on how to solve that. Okay.
Example 2.7, a ball is thrown vertically up from a rooftop at a speed of 15 meters per second. We'd like to calculate the ball's position and velocity at 1 second and 4 seconds respectively, and the ball's velocity when it's 5 meters above the railing of the roof, and the maximum height reached, and finally the ball's acceleration when it's at its maximum height. So we'll begin by looking at a diagram of the problem. So here's the rooftop from which the ball is thrown. It's going to go up, reach a maximum height, and it's thrown in such a manner that it will not hit the roof again. It will go down the side of the building and finally reach ground level. The first thing we'll need to do is choose a coordinate system. So I'm going to choose the positive y direction as up, and we're going to take y equals 0 to be at the rooftop level. Now we want to calculate in part A the position and velocity of the ball at two different times at t equal 1 second and t equal 4 seconds. Before we do that, let's look at plots of the position and velocity of the ball as a function of time. So here's the position, and notice the ball, of course, goes up to a maximum position, and then it starts to head down. So as we'll see, the time which the ball to reach the maximum height is 1.53 seconds. Before that time, it's moving up. After that time, it's moving down. The ball will pass the roof line and continue to head down to negative values, of course. The velocity of the ball begins positive 15 and heads to finally at 0 when it reaches the maximum height here. And then it passes through 0 and becomes negative as it falls down the side of the building. To execute a solution, we're simply going to use the free fall equations for the position and the velocity as a function of time. So in our coordinate system, the ball starts at y equals 0. So this is going to be 0 in the equation. This is plus 15 meters per second times t, and the acceleration in this coordinate system, of course, is minus g, since the acceleration is down. So here's the equation I get for the position as a function of time, and here's the equation for the corresponding equation for the velocity as a function of time. Again, this v naught y is plus 15 meters per second. Well, one common misconception that students have with using these equations is that somehow by hand they got to tell the equations that the ball is going to go to a maximum height and come back down. But actually that information is carried in the equations themselves, and I will not have to do anything special to find the positions and velocities after it reaches this maximum height. So let's begin by calculating its position and velocity, let's say at 1 second, and here they are. We're just plugging in to this equation and this equation. Likewise, at 4 seconds, I have these two values. For part B, I want to calculate the velocity when the ball is 5 meters above the building. There will actually be two times when it's 5 meters above the building. There'll be an initial time on its way up, and of course it's going to come back down to that same level sometime later. But since this question is not really asking for that time, I can just use the third kinematic equation that doesn't involve time, where of course the initial velocity is 15 meters per second squared, and g is the acceleration is minus g, and it's starting at y equals 0, so I can just put in y into this equation. Of course, doing that, I find that Vy squared is equal to 127 meters squared per second squared. If I take the square root of that, I actually get two solutions, a plus and a minus 11.3 meters per second. I do not want to throw out the negative solution. It is a real solution. The second one corresponds when it's coming down. So its speed on the way down at this position is equal to the speed on its way up. The same will be true at y equals 0. When it reaches back down, it gets back to the rooftop level, it will be moving down at 15 meters per second. Part C, we'd like to calculate the maximum height. And to do that, we'll use the condition that the velocity of the maximum height is going to be 0. It's starting at y equals 0, and of course the acceleration is minus g in this coordinate system. I can use this equation once again. The fact that the velocity at the maximum height is 0 is put in the left-hand side. This is 15 meters per second. Putting in all the numbers, I find that it reaches a height of 11.5 meters above the roof line. And finally, I want to calculate the ball's acceleration when it's at its maximum height. And the answer, of course, is that it's minus 9.8. And that's another common misconception in free fall. Students sometimes confuse velocity with acceleration. These things must be treated as apples and oranges. They're different quantities. The velocity starts out as positive, goes to 0 and becomes negative, but throughout the entire motion, the acceleration is simply minus 9.8 meters per second squared, because this acceleration is being caused by the force of gravity, which is always pulling down throughout the motion. And this ends example 2.7.
Okay, so let's go back. All right, so I hope the explanation already gave the
Example 2.7, a ball vertically
has
up
been
from the
clear
roof
for
line
you.
with
All right,
speed of
so
15
let's
meters
say,
per second height.
so
We do that
we
in
look,
plots of the position to negative values, of course. Up at a speed of 15 meter height here.
okay, so we look here. So we look at the problem. Okay, so it mentioned that the ball is, all right, is thrown upward with a speed of 15 meter per second. All right, and then after that, the ball is sent in free fall. Okay, so you have the graph plot on the right side. So we have, okay, so we have the motion upward is somewhere between, as you can see, somewhere between 10 to 15 meter, and then after that, the ball is going downward due to the constant acceleration due to the gravity. Okay, so that's the position of the ball, and then according to the for the graph, when you translate it as the Vy, okay, so which is the speed, okay, of course the initial speed is 15 meter per second, and then it will, okay, gradually drop. Okay, it will gradually drop until it reach at the peak. Okay, at the peak where Vy is 0. Okay, which is equals to around, okay, let's see on the graph that it said at t equals to 1.53 second. Okay, so at t equals to 1.53 second, so that's where the Vy is equals to 0. Okay, and then it changed to the negative. Okay, because now the speed, okay, will be affected by the constant acceleration due to the gravity. Okay, so at A, all right, so we have the ball position and velocity at 1 and 4. Okay, so okay, we look at here this equation. So basically we still use the first equation that we just discussed. So y, okay, because we want to know the position, so we have y equals to y naught plus v naught y t plus half ay t squared. Okay, so basically the y naught, of course, at the position initial position y naught will be 0, and then the v naught y, so you have that as 15 meter per second, all right, and t, you are not knowing it, all right, and then plus half ay. Okay, so as usual, so we have the gravity, which is the constant acceleration at a negative 9.8 meter per second squared, and then gain t squared. Okay, so we just insert, okay, 1 and 4. So when you insert 1,
y equals 0 in this course.
okay, so this is what you obtain. At t equals to 1, so you obtain y, right, 10.1. Okay, and then you have another equation, Vy. Okay, you have another equation, Vy down.
Just plugging in to this equation.
Okay, down there you have
likewise
equation.
4 seconds. I have these two values.
All right, so for the Vy,
for part B, I want to calculate the velocity when the ball is 5 meters above the building. It will actually be 2 times when it's 5 meters above the building.
okay, equals to V naught y plus AYT.
Down to that
Okay,
same level.
so the AY
sometime
still
later.
is minus 9.8, and then V naught y is 15.
Since this question is not really
So
asking for that time,
it's
you
basically you
the
just plug in those and then you obtain for the Vy. All right, and also similar for T at 4 seconds. Okay, now the position of Y will be negative. Okay, it will be negative. So when you plot the graph, so it will be like that. So actually you can do the increment. Let's say you want to plot this graph. Okay, basically assume that you don't know this graph and you want to plot this. Let's say you want to make it very precise at 0.1 interval. So you can start at t equals to 0 and then do the increment of 0.1 second. Okay, every time you are calculating the y and also the vy. Okay, that is 0, 0.1, 0.2, 0.3, 0.4 until 4. Okay, so basically you will have 40 data. All right, so once we have the 40 data, then you can plot the graph. Okay, so that's example A. All right, so you already obtain what is your ball position, which is y, and also the velocity of vy at 1 and 4. Okay, and then B, the ball's velocity when it is 5 meter above the railing. Okay, so when it is 5 meter, so what's the ball velocity? So to know the velocity, so velocity is Vy. So you use the third equation, all right? So Vy squared equals to V naught y squared plus 2 ay y minus y naught. Okay, so you have, okay, you know what is ay, what is V naught y, so you also know that. So y naught is 0. So now you want to know what is V y squared. So your y will be 5 meter. Okay, so you plug in those. All right. So basically you will get what is your Vy squared, and then square root this 127, so you obtain what is your Vy. Okay. So you notice that you will obtain the plus minus because it is a square root. Okay, how to know whether it is a positive or it is negative? Okay, so it should be positive. Okay, because the ball is still at this point. All right, as you look at the graph, okay, at 5 meter, position of 5 meter, so the time at that time it is around 0.3 or 0.4 second. Okay, you look at the graph on the left side, so you have y versus t. You look at the position y equals to 5 meter, okay, and then you have time at 0.3 or 0.4, something like that, and then transfer that 0.3 to 0.4, okay, to the right graph, okay, and you look, okay, and that's equals to Vy around 11. So that is 11.3. So the Vy should be positive 11.3 meter per second. Okay, and what C? C is the maximum height reached. Okay. Okay, so the maximum height. So
I can use this equation once again.
basically, you
In fact,
can use the same equation as B.
Zeros put in the left-hand
Okay.
side. This is 15 meters per second. Putting in all the numbers, I find that it reaches a height of 11.5 meters.
Okay, so because over here you are going to solve what is your y. Okay, you're going to solve what is your y. Okay, you know that your Vy will be 0 at the maximum height because it is at the peak, so you have a 0 speed because at that moment it is actually at a point where your Vy, okay, is going to decrease. All right, where your Vy is going to decrease. Okay, so over here, so you have the Vy equals to 0. Okay, Vy equals to 0. So basically you look at the graph, so basically it is at a point 1.5, something around 1.5 on the right side, the graph on the right side with the green straight line. Okay, so that's where the Vy equals to 0. Okay, so you will have the V naught y squared. So you're taking back the equation from B. Okay, that's this value is 15, right? Plus 2 ay. So ay is minus 9.8, and then your y naught is 0. So basically you all of that value. So now rearrange back. So you obtain y equals to v naught y squared over 2g. So you solve that, you obtain y equals to 11.5. Okay, so that's C. And then lastly, so the ball acceleration when it is at the maximum height. Okay, as you remember that, okay,
Up from a rooftop at a speed of 15 meters per second. Acceleration is simply minus 9.8 meters per second squared.
okay,
Because this acceleration is being caused by the force of gravity, which is always pulling down throughout the motion.
okay. So as mentioned by the narrator, so it says that always you remember that when the object is on the free fall, okay, so the acceleration is always minus 9.8. Okay, it's always 9.8 meter per second squared. Okay, so that's it for, all right, so that's it for the free fall. Okay, so let's move forward. Right, now we look at the velocity and position by integration. All right, so the acceleration of a car is not always constant. All right, so the motion, right, may be integrated over many small time intervals to give. Okay, so we have the equation. So before this, we note that we already have the velocity and position. So we want to know the acceleration. So we just do the differentiation. All right. So dx of the vx. So we obtain that equation. Now, let's say we already have the acceleration. Okay, now we want to know what is our velocity. Okay, so we are given with the equation of Vx equals to V naught x plus integration of Ax dt from 0 to t. Okay. And we also have the position. So x, say position x equals to x naught plus Vx dt, okay, 0 to t. Okay, so once we obtain this, okay, once we obtain this, and then we can get this. All right. So if you ask about, you are given the acceleration, and then the question asks for you to find what is x. Okay. So you do the first integration of that, and then the second integration once you obtain your Vx. Okay, so basically you replace the Vx over there. Okay, so you look at the graph there. So you have the graph of acceleration versus time. Okay, so you have the delta Vx. So the delta Vx is at a certain time, okay, a certain specific of time, a very short period of time. So you have the delta Vx, okay, which is the change in x velocity during a time interval of delta t. Okay, so that is where you have, okay, the concept of the total area under the graph of xt. Okay, so basically when you are looking at this small change, so you basically you want to find out what is the small area of that. Okay, what is the small area of that, and then you can find out what is your Vx, okay, at those t. Okay, so all right, so when that happen, okay, so basically your equation over here will change. Okay, now let's say this is time 0, okay, and then this is time 1, 2, 3, 4, 5, 6, and 7. Okay, so your Vx from time 3 to 4, so you basically change. So this is will be 3, and then this is will be 4. Okay, so you know that what is your acceleration during that time. Okay, so basically you know what is the acceleration during the time. So you insert that, right? So you insert that, and then so you have the what is the initial velocity. So let's say the initial velocity is given, right? And then you can now determine what is your Vx. All right. So that's how we do need to find out what is our velocity and position from the acceleration. Okay, from there we will look further on the problem from the tutorial. Maybe, okay, so because tomorrow it will be a lab session, so we will look again at the tutorial on the next week. Okay, so that is for the chapter 2. Okay. All right, so we are going to continue with the chapter 3. Give me few seconds. Give me a few minutes. I'm going to share you with the chapter 3 slide. Okay, you got the slide. So I just shared to the WhatsApp group. Do you guys get that?
Yes, Doctor.
Okay. Okay, so basically in the chapter 3, you will have the motion. All right, you will learn about the motion now in the 2 and 3 dimension. All right, so you just discuss about the motion and the dimension in 1D. All right, now we will discuss that in 2D and also the 3D. Okay, so this is the learning outcome for this chapter. So you should learn about on how to use the vectors to and velocity. All right, and then to find the vector acceleration. Okay, so the problem that involve curved path followed by a projectile, analyze motion in circular path, and then relate the velocities as a moving object as seen from two different frames of reference. Okay. All right, let's say you are throwing a ball. Okay, let's say you are playing a baseball, or let's say you can also play basketball, right? So, or you are playing soccer. So when you kick the ball up, of course, the ball will follow a projectile motion. Okay, so how do you describe that? Okay, and then let's say you are riding a roller coaster. Okay, so it has a track. So let's say the track is curved. All right. So how do you describe the motion of that roller coaster? Okay. So consider back that. Right. So that example. So we look on how to solve those problems. Okay. So let's say we revise back the vector. Okay. So before this, we learn on how to solve the product of vector. Okay. So now we are introduced with the position vector. So the position vector from the origin, okay, let's say you look at the figure there, to a certain point P has three components, X, Y, and Z. Okay. All right. So it has coordinate of X, Y, and Z, and then the position vector is the one that is projecting to the P. Okay. Over here it is R. Okay. This is the position vector. Okay, so this position vector will be described by, okay, by the vector of x, y, and z, which is over here. We define that in terms of I, j, and k. All right, so that is the position vector. Okay, so over here, the velocity can be defined as the average velocity as the displacement divided by the time interval. So that's for the average velocity. So let's say we are looking at the first position at R1, for example, and then going to the R2. Okay, for example, if you look back over here, let's say we are considering, let's say over here is R equals to 0, and then here is R equals to 1. Okay, so we are measuring that. So what is the delta R? Then over time, specific time interval. So once you obtain that, so that is the average velocity. And then what is the instantaneous velocity? So as the similar concept, so we reintroduce again, but this is for the 2D. Okay, it is the instantaneous rate of change of position with time. So you have limit delta t equals to 0, and then delta r over delta t. Okay, so it is similar like the 1D instantaneous velocity, except that now r is the vector. Okay. So, okay, let's say we look at an example. So we want to define what is the velocity, or is the average velocity between 2 points, okay, in the displacement divided by the time interval between the 2 points. Okay, and then it has the same direction as the displacement. Okay, let's say you have one vector, okay, at the P1. Okay, you want to know what is the average velocity between point 1 to point 2. So between point 1 over here to point 2. Right, so first you must know what is the position vector at P1. So the position vector at P1 is defined by the R1, and then you also needs to know what is the position vector at P2, which is defined by R2. So and then you use the equation V average, okay, equals to delta R. So the delta R will be R2 minus R1 over Okay, let's say at P1, position time is T1 and P2 is T2. So the delta T will be T2 minus T1. So you obtain what is the average velocity. Okay, so the instantaneous velocity is the instantaneous rate of change of position vector with respect to time. So the components of this instantaneous velocity are given by this. All right, so you have in 3 dimension. All right, so you have Vx, Vy, and Vz. Okay, so let's have a look at the graph over here. So we have, okay, let's say we have the V. Okay, we have V, and then over here it is in terms of Y and X. So this V is actually the vector defined by the vector of Vy and also vector of Vx. Okay, it is projected at a certain angle alpha. Okay, so that's instantaneous velocity. Let's say is describing for this projectile motion. So the curve, right? The curve over here to that. So basically, just want to know, okay, the tangent component of that. The tangent component of that. So that's you define the instantaneous velocity during that specific time. Okay. All right. So we look at the example.
In example 3.1, a robotic vehicle is exploring the surface of Mars, and we're given the x and y components of its position explicitly as a function of time in these two equations. What we'd like to do is find the rover's coordinates and distance from the lander at t equals 2 seconds. We'd also like to find the rover's displacement and average velocity over the period from t equals 0 seconds to t equals 2 seconds, and find an expression for instantaneous velocity at any time. So we begin with a schematic of the rover's trajectory. It begins here on the x-axis and moves up along this path. We're going to calculate the position at t equals 0, shown by this vector r0, the position at t equals 1 second r1, and 2 seconds r2, along with the instantaneous velocities at these positions, shown by the green arrows. So let's begin with its position at 2 seconds. I simply put 2 into these two equations, and here are the x and y components of that position. The distance from the lander is obtained by squaring these components, adding and taking the square root. That's going to be 2.4 meters. I can write the position generally as a vector, where x in this vector is this equation and y is this equation. And this tells me the position vector at any time. So I can calculate it at t equals 0, as shown here. Here's the two components at t equals 0. Here are the two components of position vector at t equals 2 seconds. And from these, I can get the displacement of the lander, which is r2 minus r0, with these two components. The average velocity is defined as the displacement over the time at which this displacement occurred, and I get an average velocity shown here. The instantaneous velocity as a function of time is attained by simply differentiating each of these equations. So Vx is dx dt. I get this equation, and Vy is dy dt. is this equation. I can find these velocities at t equal 2 seconds, as I've done here. I just put 2 seconds in each of these, and I get these two components. The speed at 2 seconds, of course, is the magnitude of this vector. Just as we found the magnitude here, we find the speed is the magnitude of the velocity at 2 seconds, and that's going to be 1.6 meters per second. The angle that the velocity makes at this time with respect to the positive x-axis is attained by taking the ratio of the y component of the velocity, the x component, and the arctan of that. I get minus 52 degrees. However, the x component of this velocity is actually negative, so I know this angle can't be right. The arctan only gives me the angle up to 180 degrees. So the actual angle is equal to minus 52 degrees plus 180, which is going to be 128 degrees, as shown in the diagram right here. Now, if I look at the solution, I note that the average velocity is not equal to the instantaneous velocity. In fact, if I go through and calculate the instantaneous velocity at 1 second, this will be much closer to the average velocity over the interval from 0 to 2 seconds than the instantaneous velocity at the end of that interval at 2 seconds. So V1 will be about equal to V average, because V1 is the middle of the interval. And this ends example 3.1.
Okay, so you got the concept? All right, so let's have a look.
Example 3.1, a robotic.
Okay, for example, over here, so the question asks, all right, a rover movement, okay? So a rover, okay, so now it's moving on the surface of Mars. So it has the x and y coordinate, which vary with time. So x is given by that equation. So 2 meter minus 0.2 meter per second t squared. Okay, y 1 meter per second. Okay, t plus 0.02 meter per second squared t cube. Okay, so now we need to find out, all right, so what is the rover's coordinate and distance. The rover's coordinate and distance from the lander at t 2 second. All right, at t 2 second. All right, at t 2 second. Okay, so we need to find out. Okay, so let's say this is the rover's path. Okay, so we have initial position. All right, initial position. So x equals to 2 meter. All right, and then y will be 0.
Here on the x-axis, it moves up along this path. We're going to calculate the position at t equals 0, shown by this vector r0. So let's begin with its position in 2 seconds. I simply put 2 into these two equations, and here are the x and y components of that position.
Okay, so look at that. So we have, okay, so we have over here, we have three different velocity. So at r0, r1, and also r2. Okay, so that's the rover's path. So we have at t0, at t1, and at t2. Okay, so according to this, so initially, so we have x0 and x2 and y0, and then when at r equals to 1, so x is something around 1.7, and then y equals to 1. Okay, and then at t2 second, all right, at t2 second. So we have y, okay, we have y at somewhere around 2.2, okay, and then x is at around 0.9, okay. So how to obtain that? So basically, so we look at, okay, insert the value in this equation. So given x equals 2, okay, minus 0.25, okay, and then at t, let's say 2 second, so t 2 second, so we have x equals to 1, y, okay, y is 2.2 meter. All right, so that is actually the coordinate 1 and 1, 2.2, and then r. So what is r? The distance r is equals to, of course, you take the Euclidean distance from 0 to that position. Okay, so square root of x squared plus y squared. Okay, so you obtain the distance. Okay, and then you want to define the vector. So the vector of r. So r, okay, the vector of r equals to x I, okay, plus yj. Okay, what is your x? So your x is this one, okay, where you insert from here, and then your y is you insert from the top, which is 2.2. Okay, so basically, so that is your r. Okay, so you have over here, this is at r naught. Okay, r naught. Okay, r naught when your t is 0. So of course you have r naught or r0 is equals to 2i plus 0j, which is just 2i. And then okay, so you need to find out, okay, this is for the question B. All right, so you need to find out what is the rover's displacement and the average velocity vectors for the interval t equals to 0 to t to 2 seconds. Okay, displacement you need to find out at this position to that position. Okay, so you need to find out what is the delta r. So the delta r between this point to that point. Okay, so basically you need to find out what is the difference between vector r2 with r0. So basically that vector r2 minus vector r0. Okay, so you find out what is your vector r2. So you are using the same equation as this one, okay, at r0. So you obtain r2 equals to 1i, sorry, yes, 1i plus 2.2j. Okay, and
From these, I can get the displacement of the lander, which is R2 minus
okay,
R0.
so it is minus I plus 2.2j. So
The
that's
average velocity is defined as the
displacement.
displacement over the time at which it
And then the
this
average
displacement occurred.
velocity, okay, is delta r over delta t. So delta t is 2, all right, because 2 minus 0. Okay, so basically the answer is 0.5 I plus 1.1 J.
And I get an average
So
velocity.
that's for B. All right.
The instantaneous velocity of
So
motion
C,
obtained by
now
simplifying
we
the
want
change
to
in
find
this
out
equation.
what is the general expression for the rover's instantaneous velocity vector V. All right, express V at t equals to 2 seconds. Okay, at 2 seconds. All right, so we have the instantaneous velocity. So given that Vx equals to dx over dt, okay. All right, so you look there. So we have the dx, okay, the displacement, right, is at 0.25 minus 0.25. Okay, so it's basically the equation you took from the equation over there. Okay, from the equation, so you obtain that. So basically you reverse that. Okay, you differentiate that, so you got the dx over dt. So you look at x equals to 2 minus 0.25 t squared. Okay, when you differentiate that, so the two term will be 0. Okay, so you still retain minus 0.25 times 2t. Okay, so how you obtain Vx. And for Vy, also similar. We differentiate over t. So 1t. So when 1t, so it will be just 1 over there plus 0.025 t cube. Okay, so the t cube will be 3t squared. So you times that with 0.025. So you obtain what is your Vy. Okay. And then at 2 seconds, okay, V at 2 seconds. So you replace that. Okay, you replace that value. Okay, so you obtain that V at 2 seconds will be Vx at 2 seconds is minus 1.
I get these two components.
Okay.
The speed at 2 seconds
And then
versus the magnitude.
for y, Vy, so you replace that t also with 2 seconds, and then you obtain Vy equals to 1.3 meter per second. Okay, and then so you have the x and y component. So you need to find out, okay, what is the, because it asks you about the magnitude and direction. Okay, so you need to find out the vector. All right, so you first find out what is the magnitude. The magnitude, so as equation A, okay, so as equation A, so you find out what is R. Okay, let's say in equation A you find out what is R. So here we have V. So V equals to square root V x squared plus Vy squared. Okay, so you obtain that. So you obtain what is the magnitude. And then to obtain the direction, okay, in terms of vector, okay, the direction will be, okay, minus 52 degree. Okay, because you need to find out, when you draw the vector. Okay, let's say you have the Vx. Vx, okay, is on the negative add side because it's -1, and then Vy will be positive. Okay, so your vector, okay, because you are taking that as a negative term, all right, so your Vx negative term, so the inverse tangent of that, so you obtain as the -52. Okay, but you need to remember that it is on the second quadrant. Okay, it is on the second quadrant, so you need to plus that with the 180. Okay, with the 180,
I go through and calculate
you
the
obtain that
instantaneous
theta.
velocity.
Okay, you
at
obtain
1
that
second.
theta equals
This
to
will be much closer to the
128
average velocity
degree.
over the interval from 0 to 2 seconds than the instantaneous velocity at
Okay,
1, because V1 is the middle of the interval.
all right.
And this ends example 3.1.
Okay, so that's it. So it is clear so far. You guys still okay? Any questions so far?
Okay, doctor.
All right, it's good. Okay, so now we look at the acceleration. Okay, the acceleration describes how the velocity changes. Okay, so you look at the car there. So we have the car moving at point P1 to point P2. So at different V. Okay. So whenever it is at a corner, all right, of course the car will slowing down the speed, all right. So over here it is said that the instantaneous velocity changes in both magnitude and direction. Okay, so now we can define what is the average acceleration. So like the average velocity, so we have now for the average acceleration is delta v over t over delta t. Okay, so we have the vector of v2 minus vector v1. Okay, and the instantaneous acceleration we have d v. Okay, so v is the vector of the velocity divided with the dt. Okay, so that's about the average acceleration and the instantaneous acceleration. So let's look at the example. So we have the changes in the velocity between 2 points. Okay, is determined by the vector subtraction. Okay, so we look back at the problem of the car. So we have V1 and V2. Okay, so we have V1 and V2. So we combine that vector, and then we notice that the delta, okay, so from V1 to V2. Now, because, so it's not moving from V2 to V1, because now the velocity change, all right? The velocity, of course, at V2 will be higher than V1. All right, so V2 will be minus V1. Okay. And then we find out that the average acceleration is the delta V over T. So we already have the delta V, so which is V2 minus V1, and then divide with the time at P1 and also P2. Okay. And notice that the average acceleration has the same direction as the change in velocity. Okay. If A average have the same direction as the delta V. So that's the direction of the average acceleration. For the instantaneous acceleration, okay, so we look at the tangent of the path of the particle path, all right? But the instantaneous, okay, instantaneous acceleration over here does not have to be tangent to the path. Okay, so it's a little bit different. Okay, if the path is curved, the acceleration points toward the concave inside the path. Okay, it is concave inside of the path. Okay, you look over here at this figure. So, if usual, we have this tangent. Okay, we have this tangent for finding out what is the acceleration or the instantaneous velocity. But now we want to figure out what is our instantaneous acceleration for the 2D motion. So the acceleration will be pointing towards that. Okay, it will be pointing towards that. All right, so that's how is the instantaneous acceleration is defined for the 2D motion. Okay, but if the trajectory is a straight line, okay, but if the trajectory is a straight line, the acceleration is tangent to the trajectory. So it is a little bit difficult to determine that, but as you need to remember, so let's say we have two concept over here. Let's say a curved path and also a straight line. So for a curved path, the average, the instantaneous acceleration is pointing inside that curve. All right. But for the straight line, it will just follow the straight line. Okay. All right, so as velocity, so we have a, x, y, and z component as well. All right, so that's each component of the instantaneous vector acceleration vector ax, ay, and az. Okay, for example, we have the archery competition. So the archer want to shoot an arrow, okay, in the given direction. Okay, so the acceleration is going to point towards that. Okay, so the vector will be in both x and y component. All right, so the velocity and acceleration vector of a particle moving through a point P on a curved path So it has a constant speed, right? Okay, but the acceleration, as we just mentioned, for the curve path, it will be pointed inside that curve. All right. Okay. And then the velocity and acceleration vectors of a particle moving through a point P on a curved path have an increasing speed. So when the speed increase, okay, so now the acceleration will also move upward. Okay, the acceleration vector will move upward. But when the on the path the acceleration the velocity decrease, so the vector A, okay, will also pointing more towards downwards. Okay, so that's the concept. So when the acceleration when the velocity increase, vector A pointing will be more upward, okay, more upward inside the curve. But when the velocity decreases, the acceleration vector will point inside the curve, but going more to the downwards. Okay. All right. So for the arrow problem, we need to describe that in terms of the projectile motion. Okay. So a projectile is any object given an initial velocity that then follows a path determined by the effects of gravity and air resistance. Okay. In the projectile motion, it has the effect of gravity, which is 9.8 meter per second, and also the air resistance. Okay, begin by neglecting resistance and the curvature and rotation of the Earth. Okay, so when we are solving this projectile motion, so we neglect the resistance and also the curvature and rotation of the Earth. So for example, over here, so we have a projectile move in a vertical plane that contains the initial velocity vector v0, alright, and then its trajectory depends only on v0 and on the downward acceleration due to the gravity. Okay. Alright, so your A vector will point downward. Okay. Let's say we look at two different examples over here. Okay, so we have two balls. So the red balls and the yellow ball. Okay, and then we look. So we have the stroke mark over there. So at specific time interval. So we look horizontally. So we can analyze the projectile motion as a horizontal motion with constant velocity and vertical motion. Okay, with constant velocity and vertical motion, and also with a constant acceleration. Okay, we look at example.
In this demonstration, I have two tracks. Initially, they have the same slope, So the two balls that I will place on them will accelerate at the same rate. In this area here, they still have the same slope. And then after the hill, they still have the same slope. So the only difference between the two tracks is this downhill and this uphill. So the question is, when I release the two balls at the same time, which will reach the end of the track first? Will it be the ball on the yellow track? Will it be the ball on the red track? Or will they finish at the same time?
Okay, so what is your guess? Anyone want to answer that? So we have two. Okay, so what's the answer? Will be at the same time? Or
Probably.
pardon? It will be at the same time, or the ball on red track will finish first, or the ball on the straight yellow track will finish first.
The answer is B.
The answer is B. B, C, or A? So who vote for A?
I think B.
Okay, Almin said B. Okay, who said A? You can raise your hand. I want to know what is the majority answer. A on the yellow track, B on the red track, okay, C at the same time. Okay, raise your hand for A. Okay, nobody choose A. Okay, raise your hand for B. Okay, there are 4 people. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 10 of you vote for B. So, and the rest, C. Who said it's C? Okay, Kaliang. Okay, Jai said C. Okay, so, all right, so 4 of you. Okay, so, okay, 5 of you. So let's see who's correct. Okay, because of the majority, okay, majority is giving the answer for B. Okay, but all right, so we vote for B, and let's see. All right.
So as you can see, the ball on the red track finished first.
Okay,
This
so
is
you got
because
B.
when it hit
B
this
is the correct answer.
downhill area, it had a greater speed when it reached this region. It's still accelerating at the same rate as the ball on the yellow track, but it had a greater velocity along this segment. When it came back up the hill, it slowed down to a velocity equal to the velocity of the ball on the yellow track once the ball on the yellow track reached this point. But by the time the ball on the yellow track reached this point, the ball on the red track was already way ahead and finished first.
Okay, I hope that is clear. All right. So we look.
In this demonstration, so as you can see,
Okay, the point is here. So where the ball on the red track will accelerate further. So it's going down the hill, so it will increase the acceleration of the ball. And then over here, it will, on the straight line, on down of the hill, it will have the greater speed compared to the ball on the yellow. Okay, that's how it takes the advantage of that, and then finally, when it's going up again, the speed will be again similar, but at that time, the ball on the red track is already ahead of the ball on the yellow track. So good. So because majority of you got the correct answer, so the ball on the red track finish first. Okay. Okay, we're going to look for another example. All right, so now we are considering the projectile motion. Okay, so it said that the projectile is a combination of horizontal motion with constant velocity and vertical motion with constant acceleration. So we look at this second video.
Here I have a low friction cart that has an accessory mounted on it, which will shoot this ball vertically when it reaches this trigger. Just like so. It falls back in the cup here. Now, with this experiment, I'm going to raise this end of the track and let the cart roll down the ramp, firing the ball when it reaches the trigger. The question is, where will the ball land after it is shot out of the cart? Will it land in front of the cart, back in the cart, or behind the cart?
Okay, now you have the second question. Okay, now when there is an incline, when it's on an inclined track, so the ball will be shoot out when it reach at the point over here. Okay, and okay, at a certain time, and then the question asks for where the ball will land. Okay, is it front of the cart? Okay, this cart that is held by this teacher, or before that, okay, behind the cart, or inside the cart. Okay, so what's your answer? A, B, or C? Okay, so who choose A? So let's vote. So A is in front of the cart. Okay, nobody choose A. Okay. And B, who choose B? So who vote for B? Nobody votes for B. And the last one, behind the cart, C. So who vote for C? Any of you?
I think the answer is A, doctor.
A. Okay. Okay, so okay, again, who vote for A? Please raise your hand. Okay, 3 of you. Okay, 4. All right. Okay, B. So who vote for B? Raise your hand. Nobody. And C, behind the cart. Who vote for C? Nobody responds. Okay, so you're not sure what's the answer. So as your friend said, so majority of you choose A for the answer. So let's have a look. Okay, Atika, you choose A, B, or C?
C, Doctor.
C. Okay.
Yeah.
Alright, so okay, majority of you choose A, so let's choose A first. Okay, let's see what's the answer.
So as you can see, the ball landed back in the cart. Even though the cart was accelerating down the ramp, and the ball, once it left the cart, had a constant velocity v in this direction.
It is
it still
interesting, is it?
shot forward with enough of an angle that it could
So
land.
none of your answers are correct. So it is actually the ball again reach going back inside the cart. Let's see what he explains.
Here I have a low friction cart that has an accessory mounted on it, which will shoot this ball back in the cart or behind. Here I have a low friction cart that has an So as you can see, the ball landed back in the cart. Even though the cart was accelerating down the ramp, and the ball, once it left the cart, had a constant velocity v in this direction, it was still shot forward with enough of an angle that it could land back in the cart.
Okay, the reason is because even though the cart is moving decline to the slope, all right, and at the same time the ball is having the projectile motion. Okay, the ball is having the projectile motion, and one more important thing to note that it accelerates at the same time as the time of the acceleration of the cart. So that's why, so the ball going back inside the cart. Okay. All right, so we're going to continue further on the projectile motion on Thursday, or maybe if, yeah, it should be on Thursday. All right, so tomorrow we will have the lab session. So I stop here for today. So as usual, so let's take the attendance for today. So let's turn on your camera. If you have any further question, you can let me know later. All right. Okay, I'm counting from 10. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Smile, everyone. Okay. All right, so that's it for today. So I'm gonna see you on Thursday. Any question, let me know. All right, so make sure you have already finished with your tutorial question. I will open the Putra Plus submission letter. Okay, so it's due. So that one will be due by tomorrow. So you need to submit by tomorrow the tutorial that was given last week. Okay. So any other question before we dismiss? No question? All right. So that's good. So enjoy the rest of the day. Okay. Okay. See you tomorrow during the lab session.
Thank you, doctor.
Thank you,
Okay.
Doctor.
Thank you, Doctor.
Thank you, doctor.
Doctor.
Okay, welcome.